Coming up on this episode of the IoT Inc. Business Show.
50 sensors, a few surrounding intersections, a bunch of things we have no idea whether or not they're useful, but they turn out to be. For example, we get to see the software on the traffic lights manipulate register values, and so we get really rich contextual information from every intersection. And then what we're doing is, because it's time series, you have some window of time. Okay, so we're using a CNN. A CNN doesn't have a notion of time in it, but you're basically replaying historical data as additional inputs.
Convoluted neural networks, or CNNs, are a type of AI typically used in computer vision to process images. But they're also applicable to process the time series data we typically get from sensors in IoT. In this episode of the IoT Show, I speak with Simon Crosby about how these CNNs can be used to make predictions about the future and reduce the massive amounts of data we collect to just the important stuff.
All this and more on this episode of the IoT Inc. Business Show. The people, the business, and the technology of the next generation internet. This is the IoT Inc. Business Show. And now, here's your host, Bruce Sinclair.
Hello and welcome to the IoT Inc. Business Show. This show is made possible by sales of my book, IoT Inc., published by McGraw-Hill, and the IoT Inc. Certified IoT Professional, or ICIP, online training and certification program. Become a certified IoT professional by completing the program's 3 courses: ICIP Technology, ICIP Business, and ICIP Strategy and Digital Transformation. Details of which can be found at www.iot-inc.com. That's www.iot-inc.com. With me today on the IoT Show is Simon Crosby. Simon is the CTO of Swim.AI after being CTO of numerous other companies and being named one of InfoWorld's top 25 CTOs in 2007. Simon has also been a tenured faculty member at the University of Cambridge. Simon, welcome to the show.
Thank you. It's great to be here. So
where did the name Swim.AI come from?
Well, the swim bit is the following. It's software in motion. And so, you've heard of this concept of data gravity, right? Which is that where data is, software tends to end up. And we've all perhaps misguidedly thought that if all the data is in the cloud, then the apps will move to cloud too. Actually, the swim notion is similar to that, but if we move software dynamically to where the data is and where the resources are and do the processing in the right place, then we end up with a system where we are maximally efficient and deliver real-time results. Typically, that's right at the edge.
Okay, so swim is swimming to the edge, and it kind of made sense just in terms of all the metaphors used in data science. We've got our data streaming, our data pools, our data lakes, and so forth. So I thought it was something related to that, I guess.
I keep on telling my friends at Microsoft they should call it the Azure Data Pond, not the data lake, because if we do this right, then we'll process the data at the edge.
Right. Well, all right. Well, I can see where your focus is. And data gravity, tell me a little bit more about that. I haven't heard of that term.
The concept isn't that new, really. Wherever data happens to be, it tends to be that the apps have to be close because moving data is hard or expensive. And so it's always been the case that, wherever we ended up with large databases or big data stores, we had to do the processing in proximity to it. In the case of the edge, there's so much data, particularly in the case of some of our customers, there's so much that there's just no possibility they could ever move the data to the cloud in the first place to do the processing. So you have to do stuff at the edge. And so the concept of data gravity, I think, is very real. But even if the data is in motion, you've got, coming off of large numbers of sensors or plants, you've got to process it at the edge.
Yeah, one of our classics podcasts, and it was entitled "To Be or Not to Be a Data Hoarder," and we did talk about this at length in the sense of the costs and the benefits, and we're going to talk about it today as well. But the costs and benefits of doing local processing versus doing some sort of centralized processing or doing something halfway in between. But why don't you tell everybody a little bit about your background? I know lots of CTO, and it sounds like Edge, but in particular around AI and IoT.
Well, way back when, my PhD is in basically applied probability and systems. So okay. This for me it's what I do. I've taken this very interesting detour building cool systems. So I was the CTO at ZenSource. We built the Zen hypervisor and spent a bunch of time, doing cloudy things. Then took that concept and used virtualization for security in Bromium. And now I'm getting back to my roots as essentially an applied probabilist. It's fun.
Yeah, and I guess there hasn't been too many changes in probabilistic or statistical, for that matter, theories, right, since you left it last?
Sure, though the field of machine learning is moving extraordinarily fast. And I think that's one of the key requirements as we address the edge, is that if we think we can process stuff at the edge, we have to be agile in terms of bringing the latest and best algorithms to play at any point in time. That is, whereas historically we've always said, buy some software, install it and run it forever, and the edge tends to be less agile than the core. We can't afford to do that anymore because new techniques are being invented all the times, and we should be able to deploy them dynamically into the fabric wherever our data happens to be arriving. So if we have some data scientists who has some new thing they want to try out, cool, let them try it. Let them try it right now, and bind that onto a running data stream and figure out what's going on. Mm-hmm. So it's a really important concept because this field is moving so well now.
Now, talk to me a little bit more about machine learning. One, I want to understand your definition of it with respect to advanced analytics, and then I want to understand what you think of it, in particular, what forms of machine learning are you able and potentially not able to do on the edge?
Well, so machine learning machine learning and AI are too often abused as terms in marketing. What's important is in the streaming analytics world, where you're dealing with data that's come at you on the fly, there's a ton of tools which are just available related to dynamically figuring out a regression on incomplete or potentially infinite data. Many of these techniques have been around forever, and tools like sketching and so on will be familiar to many. They continue to improve and are very powerful. But in areas where you're looking at complex, potentially even chaotic situations where there is a lot of data from a lot of sensors, and you're trying to infer the right thing to do, the application of machine learning on a rich set of inputs in an attempt to predict the way the system will behave is important. And that's the case for Swim. That is, our use of it is specifically not for a particular sensor or a particular input, but for a complex system which is otherwise poorly understood, to try and predict its future behavior.
So give us a little bit more detail. Let's scratch a little bit further down. It's still pretty high level. So in particular, I want to understand machine learning. What aspects of machine learning are you using? Because that's going to help us just understand from an edge point of view. And let's start with that.
Let's make it really practical. Let's jump into a real world example.
Okay.
The city of Palo Alto in California generates about 4 terabytes a day of data. Okay, just from the sensors, 50 or so sensors per intersection. And that's getting that up to the cloud is quite a bunch of work. Now, if I set you the problem of go and work out what's going to happen for the next 5 minutes at each intersection in Palo Alto with high probability, that's a hard problem in learning, okay? So the received wisdom says, haul me a bunch of data up to the cloud. I will train some models, and then I want live data to throw at this model on the fly, okay? Different people had different views in terms of what models would be useful there. What Swim does actually is online learning, and we use in that instance a form of convolutional neural net. And convolutional neural nets are interesting because where they're frequently used in digital image processing because they capture interesting effects on multiple scales in an image. We tweak them to capture interesting effects on multiple time scales in time series data. And so what we're doing here is effectively per intersection running a CNN. The intersection basically gets all of its input data. And there are a couple of hyperparameters for this problem, but only a couple. One is how much data from the past and what other data from around you do you need. It turns out it's really useful if you know the intersections within 1,000 yards, what's going on with them. And then we throw this into an otherwise random CNN to start, so all the weights are random. And so it's just a guess. But the cool thing about time series data is you get to observe the real world. And so you can compare your guess with what actually happened and then compute a delta, which is effectively an error computation which can be transformed and backpropagated through your neural net. And so the weights are refined. So every single sample, I'll explain all that more in a sec, every sample you throw into this thing, and we get samples every second, helps both to train the system and gives you a prediction. And the error, you can track the probability distribution of that and decide when you're accurate enough, and then you're at work.
Okay, so I'm liking this. We're using CNN, and you're training, and you're making predictions for what exactly? What is it that, or maybe there's a number of different things. What are your CNNs being trained for?
So in that particular use case, so there's roughly 50 sensors per intersection, and we're predicting the future value of each one of the sensors. So effectively, the future value of every traffic light, every pedestrian crossing, every in-road loop, which is measuring whether or not there is a car there, and so on. Okay, so the standard stuff you'd find at an intersection. And that seems highly implausible. You would suspect it would be wildly inaccurate. It turns out that it's actually pretty darn good. That is, there are a couple of things which stand out in terms of the way that we do it, which make it really useful and very accurate. First of all, every intersection is trying to train itself and predict its own future. Mm-hmm. And then it presents an API, which would allow someone like Uber or Lyft or Waymo to hit up this API and say, tell me what the future holds, so they can route their cars through a city with the least delay. Second, every single sample, and we get samples every second real walk time, helps to train the system. We get to learn on a very rich set of parameters. So the input into our CNN is about 1,000 parameters. Okay, so
these are from the 50 sensors times the number of intersections.
No, 50 sensors, a few surrounding intersections, a bunch of things we have no idea whether or not they're useful, but they turn out to be. For example, we get to see the software on the traffic lights manipulate register values. We have no idea what they mean, but we throw them in there anyway, just in case. And so we get really rich contextual information from every intersection. And then what we're doing is, because it's time series, you have some window of time. Okay, so we're using a CNN. A CNN doesn't have a notion of time in it, but you're basically replaying historical data as additional inputs, right?
Which is where your convolution comes from.
Right. Yeah. And then with each new second, you drop out the oldest and drop in the newest, and then, hey presto, you're off to the races again, right? So you end up with roughly 1,000 inputs or so, depends on the intersection. And what the CNN does then is pick up timescale effects between neighboring intersections. Effectively, as cars leave one intersection and are predicted to show up at another, you end up with a pretty darn accurate way of predicting what's going to happen at this particular intersection. And then each one of these intersections is estimating its own error and then presenting an API which would allow a third party to query it and get a prediction for the future. And then we predict an error bound around the predictions. They are obviously weaker as you get further off into time. So what do we get? We get parallelism because every intersection is solving its own model. Mm-hmm. You get online training. You get a model which is unique and focused on a particular intersection. Yep. So we get to avoid some of the nasty effects which you can get from overfitting and underfitting if you use training data sets with particular biases in the cloud. That is, if I'm learning the neural net for university in Middlefield, I don't really care. That's all I care about, right? So I just want data for that. And overfitting and underfitting aren't really defined there because the more perfect the model is, the better.
So what I'm hearing you say, and then I guess for everyone listening right now, the convolution, why it's used in for image recognition. Remember, we've talked about the Chihuahua versus the blueberry muffin, is that it's looking at a set of pixels around a pixel. And in this case, I think, Simon, correct me if I'm wrong, you're kind of just going temporally in, so you're looking at before and after, and I don't know how many befores and after.
Right.
It's similar then too. That's why you're using the same type of algorithm. So I get that, and I understand then your inputs on the top of your CNN are going to be around 1,000 inputs from your traffic station, and then ones that feed into it because I'm assuming that's going to have an effect on it, and then some other random variables. But what's the output? That's what I'm trying to understand. I know the goal is to try to adjust. I'm assuming the goal is to try to adjust the timing of the lights to minimize some time, and I guess maybe that's somehow related to the outputs then?
Well, actually, so we're a startup, and nobody's ever going to trust a startup to change the timing of the lights, right? So that's just because that's timing critical, that's safety critical stuff. So it turns out that if I solve this problem in the cloud, pick any old cloud, it's roughly $5,000 a month in terms of function cost, lambda or function cost, plus GPU costs and everything else, plus the cost of moving this large amount of data up there, cleaning it up and everything else. Whereas, and that leaves you with a distasteful cost per intersection per month.
That's 5,000 per intersection, or 5,000 for these 4 terabytes a day of data?
For the city with roughly 100 intersections, so $50 per intersection. Sorry, wait a minute, 1,000 intersections. Okay, so $50 per intersection per month. Okay.
Okay.
And it's just too expensive. It turns out that if you can solve the problem for vastly less, then there is an interesting market. And the market is, can I expose to Uber and Waymo and Lyft and Apple and insurance companies and whoever else wants it, FedEx and UPS, the data which would allow them to hit it and just ask the question, what are you going to do? Okay? Not try and change things. Just
what is what going to do?
What is this intersection going to do? I'm Uber. I want to route this Uber through the city. I have a bunch of candidate routes. Which is the quickest?
Okay.
Okay.
So it's not adjusting it. It's just about making a prediction of what it's going to be like. So then you can adjust your route based on that data.
Correct.
Yeah. Okay, let me understand that before you go further on this, and I am interested in getting the economics and understanding this a little bit more, but I still want to understand what you're doing with the CNN. I got the inputs. I think I understand. Well, I don't understand what the outputs are. So what's the output of the CNN here?
The outputs are the predicted values of my inputs. So
okay, so it's a one-to-one matching for the number for those 1,000 to the next.
No, not the 1,000.
No.
Not the 1,000, because remember the 1,000 contains historical.
Oh, yes, of course, yeah.
Okay. So and that's key actually in the whole process for us is that we're only predicting the output
50 for the 50. Then is you're outputting then the 50. Okay,
right.
Got it.
Yeah,
got it.
Okay.
So we've got the 1,000 inputs. We're outputting the 50 outputs. Those outputs are basically going to be the state of each of those, the data state for each of those sensors. And those sensors, as you gave us a few of them, but it's going to be whether the light's red or green. It's going to be whether there's a car there. What are some other examples just so we can understand it?
Whether there is a pedestrian going to hit the pedestrian button. Oh, that one's hardest, by the way, because it's very difficult to predict when somebody's going to pop out of a store and hit a button.
Yeah.
And that's about all. But there is a possibility of adding in additional sensors as people, deploy them or in some situations where they happen to be present. But it's really, our goal there was just to try and go off literally the traffic infrastructure that is managed by the city.
Mm-hmm. Yeah, and basically modeling it.
Yeah.
I mean, that's what you're doing. You're modeling it. You're modeling with your convoluted neural network, and you're looking into the future. And how far do you look? Do you have a couple different I guess no, it's just one output then. So you just define that as one of your hyperparameters?
Yeah.
For how far in the future you look?
That's right.
Okay. Interesting. Okay, so now I think I understand then what you're, in a very high level way, I understand what you guys are doing. And that's cool. So you're making a prediction of what's going to be the state for that intersection. And then other algorithms will then use that data to then route their way through it, or whomever, I don't know what else. So you could probably do some other things with that as well. And so now you were getting into the cloud and the edge. So now this original building of the model, is this, you're saying this is also done on the edge, or are you building it and then refining it on the edge? It's all done on the edge. Okay. So maybe you can go ahead.
So the key thing here is that we aren't building it. That is, it builds itself. That is, I think it's important for the edge in general that because there is such diversity and such variance in any deployment, that we'll be able to take pretty gray data and figure out what the heck's going on. Okay, so I want to be a key requirement for us is that we really get pretty murky data. In the case of traffic lights, we get voltage swings on poles. I mean, it's just ugly stuff. And really all we want to be able to do is pick out the entities that are reporting. It turns out that in the traffic world, all the sensors for an intersection report by latitude and longitude. And so that's straightforward. What Swim does is simply detect the entity and then builds an actor. I'll call it a digital twin for that entity, okay? Mm-hmm. And so one way to think of Swim is, you've heard of distributed actor systems before, like Akka or Erlang or Orleans, which Microsoft used for Halo 4. What Swim does is it detects an entity in the data. Automatically it creates an actor, an entity, which is going to process all of the data at the edge from that thing. And that's our job, all right? So to find the entities and then to let entities deal with their own data. And so the sensor, so every time data arrives for a particular intersection, Swim just hands it off to that actor, which is really just an active object, which is stateful. And its job is to, first of all, transform it from voltages into, red, green, and yellow, and so on. and then to analyze its own data in the form of understanding its past, its present, and possibly predicting its future if it's relevant for the particular situation. In this case, it is. And so you get dramatic reduction in the amount of data simply because each one of these stateful twins, these digital twins, is processing its own data at the edge, doing transformation, reduction, and so on, and analysis. Right? The data doesn't need to be stored unless you really want it for some reason, but you don't really want to know what the traffic light state was last Tuesday morning at 8:07. You just want to know what it cares to know about its past. Okay. And so you get massive savings by having, instead of a big database with all your data in it, you have a fabric of actors, these digital twins, which are stateful and continually process their own data and present APIs, which allow you to ask them what they think about the world, right? What's the past? What's your current state? What do you think about the future? And this can be done very efficiently at the edge. And I think it's worthwhile pointing out something which we all too often forget in the rest world. Not the rest of the world, but the rest world, which is that every time I go to a database, I'm looking at a 50 millisecond round trip time and then serialization, right? Well, but that's maybe a billion CPU cycles at the edge. I can do a lot with that.
Yeah, no, you can do a lot with that, and we're also kind of constrained by the speed of light, and so we need to get our data to and from some sort of data center where that server is, and it's going to have, depending on how fast this has to be calculated, it's going to have obviously that lag state.
Right. So what Swim does really, so Swim is this distributed actor system. It basically, you point at some CPU or instance capacity, and it just grabs it and forms this fabric. It's designed to just run at the edge. And so think of it as peanut butter on your toast, smeared between the edge, which is as far as you want to go to where the data is, and the cloud. And we typically present APIs in the cloud. In this case, they're in Azure. So the Azure, Uber would go to and hit up this API in Azure to find out what's going to happen. But typically, most of the crunching gets done close to data. And Swim automatically moves the tasks around, the tasks for an actor, around in the fabric to where they are best solved. Okay, so if I happen to have an NVIDIA Jetson sitting out towards the edge, great. All the learning and stuff will just happen out there and not be moved to the cloud. Alternatively, you happen to have a bunch of fat cloud instances, it'll move it up there. But no Kubernetes required and no DevOps. Swim just instruments the capacities of the instances it's on, and then automatically moves things and moves the data to them, okay, if necessary. And so Swim basically takes all notion of where, in the sense of network bandwidth, compute resource, memory resource, storage, and so on, away from these actors. They just live in object land, and they collaborate to solve problems.
Okay. So let me just stop you there. So what I'm doing for everyone listening is I want you to abstract Swim, right, to an edge discussion. And what we're talking about here is, and you said the key word, and so I guess one question I'm going to ask you is, where is the actual CNN being created initially? Because you need to create. There has to be something there before you infer it. You put it on the edge and you run your data through it. So there has to be a model. You refer to it getting smarter. So it has to do this back propagation that you're talking about. So there's the creation and then the improvement of the CNNs for, in this particular case, and I like the term the digital twins. So using your digital twins for these intersections, are they actually being done on the intersection, or is it that being done on the cloud? Then you're sending the model down to the intersection and then just running through it.
No. So what's happening currently is that we're running on a couple of spare CPU cycles in the city data center. Okay. Because the controllers on the lights are pretty lightweight things. Perhaps that'll evolve in future, but at the moment we just sit at the track management system in the data center where we get all the live updates from the traffic infrastructure and then just process there basically on CPUs that have already been bought.
Okay, so then the network fabric that you're referring to then is going to be the city data center, the Azure cloud. That's the network fabric, and you're getting the updates from the edge that goes to the city data center. Within the city data center,
right?
You're doing your inference there, and are you building the models initially there as well, or are they being built in the Azure cloud?
No. So they're being built right there. Okay. And so here's what it is. Essentially, the entity reports, and it happens to be an intersection, and it happens to have some number of sensors. And that allows us to go and dimension a model on the fly. The model is initialized with random weights, and then we just start throwing data at it. So there's no human engagement here. Okay, and the beauty of this is that as the solution rolls out nationwide, and it currently is being rolled out nationwide, every city that upgrades their traffic management system, suddenly a whole bunch of new intersections and their predictions just show up in Azure, and we do nothing. Okay.
Right. So to understand what you're saying here is that you are then improving. So there's a process for everyone listening of back propagation when you're using neural networks and convoluted neural networks, and what Simon's referring to as weights are the parameters that you tweak. They initially start out relatively random, but then you tweak to get closer and closer based on an error function. What's really cool here, since it's time series data, and so everyone listening, if you're in IoT, you're going to have this, so you can use the same trick. Since it's time series data, you can look at the prediction that was made, and then in the next time slice, you can look and see how far off that prediction was to the actual data. And I think that's what you're saying. Then you can go and improve your model. Then you can, now you're not going to do this at every cycle, obviously, every frequency, but you can do this at whatever frequency. And it's great because you've got great training data. Well, I don't know if that's called training data, but you've got great data because you have what you made the prediction, and then immediately you're going to get at some point in the future the actual results. So this trains these models, right? And this training is what you're talking about is happening at the city data center.
There are some interesting consequences, okay? So the model for University and Middlefield is entirely different than the model for University and Hamilton, and you cannot interchange them.
But when you say different, you mean topologically different, or what do you mean?
No, it just will turn out to be one that the model is itself, it's online learning, right? Online training.
Well, of course, it'll be different because they're in different situations, right? They're in different geographies with different types of drivers, different types of, topology of the roads and all the rest of that. That's what you mean then, right?
Exactly. Yeah.
Yeah, of course. Yeah. So, and this is what you were saying earlier, which is interesting, is that, in our definition here on the show, a digital twin consists of the original data and then the model. In this case, the model's the CNN, the Convoluted Neural Network. The original data, you may or may not keep that. It sounds like you do not even keep it, which is cool. But you are going to keep some data because that's going to be the output that you then have to send up to Azure to allow an API from an Uber, let's say, for example, to access it. Am I understanding it correctly? So then there's that. So the data that you are transferring is going to be the 50, I don't know if it's the whole 50.
Yeah, that's right.
Right? So you have the 1,000, it's going to be the 50. So instead of having to send that whole 1,000, you're reducing it to something down to the 50. You send that up to the cloud. That then can be then grabbed or hit on, like you were saying, by an API from whomever. Is that accurate?
Yeah, the key point is, in doing this, you've got a data reduction of, the order of three orders of magnitude. So it's really affordable, and you've semantically enriched it in whatever way you want, right?
By its context, is that what you mean, or what do you mean by that?
Instead of just being red, green, and blue, you have something which is of higher value. I'm predicting that, or I have some degree of confidence in, or something like that, right? Okay. And it's possible at the edge to add additional useful bits of information, like it just started raining or whatever.
Yes. So are you bringing in, of those 1,000 data sources, are using some external data like that as well in terms of the weather conditions? Because that would think that would definitely have something to do with it.
Yeah, not yet, but it's easy to do. It's easy to do once you're at the edge. And I think this is one of the values of the edge, is that if it is agile in terms of its ability to be programmed, then you can add these additional, virtual sensors, as it were, right? To do cool things.
But now that's going to be on the input layer, you're saying? So you would expand the input layer, so that's then changing the topology, or some different way?
Right, just create a new input. It's very easy.
Okay, and then that input so you increase the 1,000 to 1,001. It still goes down to the 50. Yeah. And so the topology has to change a little bit, but not necessarily the inner layer. So just out of curiosity, how deep is your CNN?
I'm not sure we've told anybody about that.
Okay. Is it 10, 100? Just order of magnitude. It's just curious for everyone to understand. This is a interesting architecture that you're talking about, because generally when we've discussed doing analytics on the edge, it's really been something very simple like windowing or anomaly detection, just very, very simple stuff. Here you're kind of doing a dance between the data centers and a bigger cloud to do some crunching, but it's interesting topology, architectural topology that I guess everyone listening to is just thinking, okay, how would I use this? How would this make sense in my situation?
Right. Yeah. So it's of the order of tens. Remember. Okay. So, our current window of time that we care about is 2 minutes.
Okay, that's how long you need to. What is that? Is that how long it takes to give you that prediction and take it back up to the cloud, or what does that mean?
No, I think if we crack this thing, the problem in general, right? Not just the traffic problem. It's reducing complex systems to rules of thumb that normal operators will be able to tell you. Right, so the traffic at a particular intersection, or how the intersection is going to behave, given that it's triggered by a stuff, is based on traffic that's pretty nearby. Okay, define me pretty nearby. Well, maybe it's 5 minutes, maybe it's 2 minutes. I don't know, but it's easy to play with, right? Okay, so we're trying to reduce these complex systems problems to just something that a normal human, like the traffic engineer for the city, could go and tweak. Okay, 5 minutes of data is enough, or whatever it happens to be. There are some other interesting notions of analysis that I want to get into, though, if you have time.
Yeah, no. So I think I just want to tie a bow on this before we move on. But for everyone listening here, Simon kind of took us through a little bit on the economics here, but around $50 per intersection.
Well, that was in the cloud, okay?
Okay. Versus,
well, under $1.
Under $1.
Sure. In fact, in the deployments we've done to date, no new CPU at all. Okay.
You are using the city's data center, right?
Yep.
So that's free. You're assuming that's free?
Well, they're running these traffic management systems, which are generally
anyway, right? Yeah. So you're just tapping into that data.
Which tapping into data, and so the key point I'm trying to make is that you make orders of magnitude improvement in terms of the amount of data you have to ship back and forth, but you also make orders of magnitude improvement in the cost of actually doing a solution. So at that point, if it costs me $1 a month, can I sell access to an API to an Uber or a Lyft or a UPS? Oh yeah, but not at $50 a month. Okay, so I think there's a whole new market for data or insights, which is possible when we can get the costs down. And I think one of the requirements for Edge is that we do it affordably, because often we're looking for marginal improvement. We're not looking for first order improvement. Okay, I'll give you when I say marginal, I mean this. I'm working with an organization that has a large number of gas compressors, and they get 70 data points per degree of rotation on each of four shafts. They all run at 1,000 RPM, 360 days a year. Okay, and that's $1 billion of capex, and they want 0.25%. Now, the amount of data that comes out of that thing is just, I mean, they tried to do Mongo. They're currently at the point of getting 2 rotations per hour. Okay. But so the amount of
even more than your 50. I don't know how many degrees of freedom there are in these, and then I don't know what the sample rate is, but so we're talking, what are we talking about? A lot more than 50 per second then, or I can't remember what your.
Yeah, 1,000 revolutions per minute times 70 data points times 4, right? It's staggering. And of course, being Mongo, it all gets converted into ASCII or something silly along the way. But the key point I'm trying to make is that if you measure the amount of information, the data, versus the benefit they're after millions of dollars. But the amount of information is sufficient to completely bury them. They can't buy hard disks fast enough. Okay, nobody can. So the key point here is that when we're looking for savings of millions of data, millions of dollars, we might be required to deal with vast amounts of data, which are quite simply not economically viable by hauling everything up to the cloud and doing it there.
Yeah, no, I'm totally with you on this, and I have a question to actually run through the tens of layers on your CNN. How long does it take to do an inference for a set of data to get those 50 outputs?
It's obviously device dependent.
Yes.
We have both CPU and GPU implementations. Okay. You're going to chuckle at this. You can do a couple of intersections very handily on a Raspberry Pi.
Nice. Really? Really? So, and you got the memory to load it? I guess the memory. So what's the size? Yeah. So tell me a little bit then about the CNN. What type of memory does it require on this Raspberry Pi? Per because it's a digital twin, so per digital twin.
No, so that isn't what we use but we played around with it, right? Mm-hmm. Actually, the perfect device is NVIDIA Jetson, because you've got a small GPU and you've got a 64-bit ARM. That's great for doing a small city, and that's a $200 device, right?
I'm sorry, what was the name of it again?
NVIDIA has a small device called the Jetson,
the Jetson. Yeah, okay.
That's in its second iteration. It has a 64-bit ARM. There's however much memory you want, but 4 or 8 gigs, and then a 256-core GPU.
Interesting. So the 48 gigs you're implying, then that's enough to do many digital twins for many traffic lights.
Oh yeah. I mean,
it's pretty big. That's
a ton. Yeah.
Yeah, that's a ton of. But I guess more the point is that when you do this in the cloud, you send up all this data in the cloud. And so getting back to our data hoarders, to be and not to be. So the whole premise of not being a data hoarder is because some point in the future, you believe, this being the company believes, that it's worth the investment to haul it up there and store it up there, because you may figure out something, you may find some gold in them there hills that you didn't expect. And if you throw away the data, that's the non-data hoarder, then you have forever lost that potential, which may never end up happening, but you've forever lost that potential value.
Yeah.
So, I mean, the data hoarder, to be or not to be, still applies here.
Sure they do.
In a sense, right?
No, absolutely they do. The problem is they don't have a budget.
So that's an important constraint. Yeah, that's right. So you may not actually. So I guess the message you're saying here, Simon, is that you may not even have, depending on and you've brought up 2 interesting use cases, but depending on the use case, you may not even have the ability to be a data hoarder. It just costs too much.
I think people are.
The way it is.
I think a lot of people are trying they're off experimenting, right? So we're in the 10th year of this. I think big data came out of the weeds about 10 years ago. And everybody thought, okay, big data is it, right? And now we're doing big data in the cloud. Yeah, whatever. Same story, but different problems. I'm all over big insights. And if it takes big data to get big insights.
Big insights, big data, okay.
But I think I'd rather, if I can get rid of the ephemeral data that is of marginal, which is of value now and for a short time period, but then ditch it, right? And do that.
And what's also important to this audience is that we are generally speaking about IoT here, and we are speaking about time series data, and that can get pretty horrendous. And yes, we've done big data in the cloud, but if your application happens to be a social network that's native to the cloud, or it happens to be, a piece of software that's native to the cloud, that's not that big of a deal. I mean, you're there. But having to then transfer that, having to take all this time series data, and that's why I wanted to speak to you guys. Really, most importantly, was the data that we collect in IoT. Not always, but it's generally going to be unstructured time series data.
Yeah,
and a lot of it. So, and you're making the point that they're using, in this case, machine learning and neural networks in particular. You can be pretty efficient, almost orders of magnitude. In saving the amount of data you have to move, and then the costs associated with it.
Right.
All right, Simon. Well, I think that's a good way to kind of wrap things up. Can you tell everyone where they can find out more about Swim.AI and more about yourself, and maybe anything else you want to tell us about?
Oh, we're at Swim.AI.
Yeah. All right.
Unsurprisingly. Thank you. This has been great. This has really been great fun.
All right. Thanks, Simon. We'll talk to you soon.
Thanks.
Okay. That was a good talk with Simon Crosby. This podcast goes vertical, deep diving into different topics each week. If you prefer a more horizontal and structured approach to learning IoT business and its orbiting technologies, check out my book IoT Inc., published by McGraw-Hill, or become a certified IoT professional by completing the ICIP training and certification program. For details, just go to www.iot-inc.com. Also go to www.iot-inc.com for an analysis of this episode, links to things that were mentioned during the episode, and very importantly, the episode's PDF transcript. Just search for the name of the episode or the guest. If you're new to this podcast, subscribe. That way you'll get every week's episode delivered straight to your device. Or, if you've been listening for a while, there are 3 ways you can support the show. You can leave a rating or a review on iTunes. Just go to iot-inc.com/iTunes. It only takes 1 click to leave a rating, a little bit longer to leave a review. You can share it on social. I'm on LinkedIn, to a lesser extent on Twitter. And of course, you can support this show by buying my book, IoT Inc., or the ICIP training and certification program. It's how I pay the bills. Next week's episode is Making Predictions about the Predictive Tech of ML with James Canton. I hope you can join me then. I'm your host, Bruce Sinclair. Thank you for listening. Until next week, may your path to IoT business be a predictable one.
You have been listening to the IoT Inc. Business Show.